Hello again, everybody. Welcome to the first of 2 days of review for our unit test on logarithms. We'll do the first 10 questions on our review paper today and then the next 10 on the following day. So have that with you as we work through these problems and try to remember what we did. Okay, so look at that first problem. You see it's log base 7 of 1 over 343. So we're looking for the exponent or the log of 7, which gives that fraction. So what we did was we assigned x equal to that log expression. So we have x equals log base 7 of the fraction. And then we wrote that in exponential form. So the base was 7, log was x, so 7 to the x power equals the fraction, 1 over 343. On our next step down, we wrote 1 over 343 as 1 over 7 to the third, because you might know that 7 to the third is 343. If not, you can check that out on your calculator. And then we wrote that right side with a negative exponent, so that's 7 to the x power equals 7 to the negative third. Remember that fraction can be written with a negative exponent. And then once we got both sides with 7 to a power, we just set those powers equal to each other and got x equals negative 3. And so that's the log that they were looking for. Okay. So number 2 is the same. We had to find log base 6 of 1, and so they were looking for the exponent on 6, which gives 1. So we said, let's assign x equal to that expression, and then write it as an exponential equation. So 6 to the x power, the base of 6, the log is x, equals the anti-log. So 6 to the x power is equal to 1, and we remember that anything to the 0 power is 1, so we'll just write x equals 0 for that. Okay. Next two problems are to condense the log expression into a single log. So we have to end up with just a single log from the two log terms that you see there. And so we're going to use two of the properties of logs that we learned about. The first one is, notice that each of those terms has a multiplier of 20 in the first term and 5 in the second. So those multipliers will become exponents on 5 and 12, like you see in the second step there. And that's the log of a power backwards. It's the log of that power property backwards. So after we then use those multipliers as exponents, we notice that we have two single logs there that are subtracted. And when logs are subtracted, we should remember that we're now talking about the log of a quotient property used backwards. So I'm going to rewrite that as a single log. So log of the 5 to the 20 over 12 to the 5th. Because the logs are subtracted, their anti-logs are divided. And so there's your condensing into a single log. It's not important that we figure out what those numbers are. We'll just leave it like that because the point was to condense into a single log. Number 4 is next, very similar, except you got a plus sign in between the two log terms. So again, we're going to take those two multipliers, the 5 and the 25, and write them as exponents on the x and the y. It's the log of a power property backwards. Once you've done that, you see that those logs are added. And so when we condense into a single log, we're going to multiply those anti-logs. So that's log base 4 of x to the 5th times y to the 25th. We've condensed into a single log using two different properties, so that's what they require. The next two problems are to go the opposite way, expand each logarithm. So you're starting with a single log, and you're going to expand into more than one log. So our problem is log base 9, expand log base 9 of a to the 5th times b to the 6th. So we see we have a log of a product. So we're going to apply the log of a product property. So that says take the log of the first factor, so log base 9 of a to the 5th, plus log base 9 of b to the 6th. So now we've got it into two logs by expanding, but we're not done because we have now in each term a log of a power. We got to use that other property to go one more step. So the first term then is written as 5 times the log base 9 of a plus 6 times the log base 9 of b. So now we've got it fully expanded into two logs, two different properties used in that case. Number 6 is very similar, except this time we have actually 3 factors in the anti-log. So we have log base 3 of x times y times z to the sixth. So this time when we expand, we're going to end up with 3 terms, each with their own log, which are added. So we're going to rewrite that as log base 3 of x plus log base 3 of y plus log base 3 of z to the sixth. Notice that the first 2 terms are finished. They don't expand anymore, but the third term we can expand one more time using log of a power property. So we bring that 6 exponent down as a multiplier times log base 3 of z. And there's your complete expansion in number 6. Okay, number seven and 8 are graphs. And so with the first one, number 7, you can tell by the fraction raised to the power is an exponential decay problem. That's the L-shaped graph. And then that number 8 is an exponential growth problem, the J-shape. And we're going to graph both those. Remember, what we did as a strategy to graph these was we made the parent function simply because it was easier to make that table. And then once we had that parent function on the graph paper, we then just move it down, each point move down 1 square, and then that's the graph that they require. So our function in number 7 is y equals 1/2 to the x power minus 1. So the parent function is just the y equals 1/2 to the x part. And then those points will be moved down 1. So we made a table that you should be able to use right there. From x goes from -3 to +3. And we started from the bottom there and just use 1/2 to the third, which is 1/8, 1/2 to the second, which is 1/4, 1/2 to the first, which is 1/2, 1/2 to 0, remember, is 1. And then you're noticing the pattern there that as you go from bottom to top of that table, the y coordinate is doubling. But I also did a little example on the side there of how to use a negative exponent with a fraction. So 1/2 to the -1 power, remember, is 1 over 1/2 to the +1 power. And then ask yourself how many times 1/2 goes into 1, which is 2. And then so that's going to be the y coordinate for that -1. And then -2 goes with 4 and -3 goes with 8. So there's your table for the parent function. So I put those points in black on the graph. You can see I didn't draw the graph there. I didn't really need to, because remember, I have to just lower each of those points by 1. And so when I did that, I just went down 1 square for each of the black points. I got the red point there, and then I connected the red points. And you see that L-shaped exponential decay graph right there. They're not asking us to do the domain and range, but you could, but just by looking at the graph. I've also put this on Desmos because it tends to do a better job of graphing than me, but I wanted to show you step by step how that works, since you won't have Desmos available to you when you take your test. So here's the parent function that we just graphed. All right, y equals 1/2 to the x, and then this next one should just be the exact same graph moved down 1. So there you go. All right. Okay, let's take a look at that number 8 there. That's exponential growth. Here we have y equals 3 to the x minus 1 power plus 1. So here we know that once we graph that parent function, we're just going to take those points and move them to the right 1 and up 1. To the right 1 because of the x minus 1 exponent, and up 1 because of the plus 1 on the end. So a reasonable table for this would be choosing values of x from -2 to +2, because remember, we're just graphing the parent function right now. So if I start from the bottom of the table, just to make it easier to get started, 3 squared is 9, 3 to the first is 3, 3 to the 0 is 1. Now you're into your negative exponents, so 3 to the -1 is 1/3, and 3 to the -2 is 1/9. So again, I put those black points there on the graph. You can see them there. I didn't draw the graph through there because I didn't need to. I need just take each one of those and move each point to the right 1 and up 1. That's where you're seeing the red points. And then once I've drawn the red points on there, then we can go ahead and connect those, and that's the graph they require. Okay, I also put that on Desmos so you can see a better look at that. So let's take a look at those. So there's your 3 to the x. And then in this second equation where we changed some numbers there, we moved to the right 1 and up 1. And You can see the effect when Desmos graphs that in the red graph there. Okay, so that's exponential growth. And remember, you won't have Desmos. You're going to have to make these tables by yourself. So do the parent function first, and then just move points after that. Okay, this next one's tricky, probably the trickiest graph we have on this assignment. You're graphing a log function. So the log function that we're graphing is y equals log base 5 of x plus 4 minus 4 on the end. So here's what we did. You probably don't remember this. It's been a while, but to graph log functions, the easiest way to do that was to graph the inverse of that log function first. Or at least make a table for that inverse first. And then switch the x and y coordinates, because remember, inverse functions are simply functions with the x and y coordinates switched. So we'll make a table for the inverse function. We'll switch those ordered pairs, and then we'll graph those switched ordered pairs. That will be then the points on the parent log function. Once we have the parent log function, then we can just move all those points to the left 4 and down 4 like we always do. Okay, so the parent function for number 9 is y equals log base 5 of x. So remember, we're going to find the inverse of that and get those points and then switch those points. So the inverse of that, remember, what we do is we switch x and y. So we have x equals log base 5 of y. We switch x and y. Now we're going to write that as an exponential equation. 5 to the x power is equal to y. Or if you like, y equals 5 to the x. So that is the inverse function, remember, because we switched x and y, and it's just simply easier to make a table for that inverse function than it is for the one they gave us. So here's our table. We're only going to be able to use 3 points of this because of our base 5 there. The numbers get large very quickly. So we're only going to be able to use -1, 0, and 1 for that. Okay, so I'll start at the bottom. 5 to the first is 5. 5 to the 0 is 1. And 5 to the -1 is 1/5. Okay, so again, don't get confused on this. We're not going to graph these points. That's the inverse. We're going to reverse those ordered pairs to give us, let me separate this out so you're not confused here. Those are the inverse. That's not what we want. We're going to switch them now. So we're going to have 1/5 go with -1. 1 goes 0. And 5 go with 1. Okay, those are the points in that second table that are on the graph of the parent function, which I'm circling right now. Those points in the second table are on the graph of the parent function, which when we put them on there, then we're going to move them left 4 and down 4. The first table we did simply because it was easier to make that table for the inverse, and then we switched the ordered pairs. Okay, so we just got 3 points on our graph, so it looks like we got 5 with 1. So 1, 2, 3, 4, 5 with 1. 1 with 0. And 1/5 with -1. So here's the graph of that. Actually, you know, I'm not going to graph that. I'm just going to, I'll graph that. So that's a typical log function there. I can't describe that as any kind of a letter that we know, but that's a typical log function, and it doesn't matter what base you're talking about. Okay, so those 3 points that we made, remember, now we're going to be shifted left 4 and down 4. So starting with this upper point. So I'll start with this lower point here. So we got 1, 2, 3, 4, 1, 2, 3, 4. So there's the new point for that first one. This one that was at 1, 0, now I'm going to go left 4 and down 4. So 1, 2, 3, 4, 1, 2, 3, 4. And then this one here was at 5, 1 is going to go 1, 2, 3, 4, 1, 2, 3, 4. So here's our graph. Okay. So let me show you that on, and they do want domain and range on here. So let's talk about that a little bit. So you're looking at the red graph. The domain is the x. Notice in the black graph, the parent function, we could have any number x greater than 0, strictly greater than 0. Now you can see that as x gets bigger, the y gets bigger. But once x gets closer to the y-axis, it's never going to touch. The y-axis is an asymptote there. So x can never be 0 or less. Remember, we talked about briefly this parent function the domain of log function. Its input can never be 0. Its input can never be negative because there is no power of 5 which gives you 0, and there is no power of 5 which gives you a negative number. So this input, this domain of the log function, is only positive numbers. But when you move this black graph over to left now, the one that they're asking for is x is greater than -4, because everything just got shifted to the left 4. The range of both of those graphs, the parent and the one they request, is, you can see that the y coordinates will be any real number, because as x gets bigger, y gets bigger. As x goes less and less and less, y is going downhill very quickly. So y can be any real number, and y can be 0 and positive and negative. So that's the trickiest problem on there. You might need to rewind that video and see how that explanation works. Okay, we got one more, and that's number 10 today. So this is just simply to find the inverse, and we've already done that in the previous problem. So number 10, they're giving us y equals log base 3 of x minus 5. Notice the x minus 5 is not in parentheses. That's important. Okay, so to find the inverse, remember we had this 4-step process, but really now it's a 2-step process because we don't have this in terms of f of x. So the 2-step process is simply to switch the x and y. So this will be x equals log base 3 of y minus 5, and then solve for y. So the way we did that was we first subtracted, or actually added 5 to both sides. So we had x plus 5 equals log base 3 of y. And then we wrote that as an exponential equation. So 3 to the x plus 5 power is equal to y. And so if you'd like to rewrite that on the other direction, y equals 3 to the x plus 5 power. Okay, so because we started out with the equation they gave us, we switched x and y and then solved for y. We now have inverse functions. These are two inverse functions, and just as a review, inverse functions are functions where if you take any point that makes the first equation true and reverse the ordered pairs, x and y, that point will make the inverse true. And then regarding the graphs of them, remember, they are reflections of each other in the line y equal x, if you were to graph them. All right, that's it for today, and we'll do the second half of the review next time, so enjoy and happy reviewing.